Okay, let's talk about what's happening inside those wires that we're looking at when there's current flowing through them. So I have two situations here. Electrostatic equilibrium, that's kind of like maybe there's no current, versus not electrostatic equilibrium when there is an electric current. So here, maybe there's no battery or nothing pushing the electrons through. Now what's going to happen here, the electrons we said are kind of like a gas, they just bounce all over the place. So this is just an illustration. Electric field is zero in the conductor, that the electrons are just bouncing around in random orientations here. I'll just draw a few electrons here. So Matt. Right, so what I have here is they're just traveling straight lines. They go for some distance, they bounce off of an atom and then go a different direction. Right, so they're just kind of. If I were to look at any one electron and plot its velocity graph versus time, it will look like this. Roughly, I'm just kind of making something up. But it's kind of getting to a point here. So velocity in the x direction versus t, what I have is it's constant. It hits an atom, now it's going some other direction. Constant, right? It's not accelerating or changing, but that velocity just kind of changes at random intervals. But notice that they're all kind of centered around v equals 0. They're just as likely to be going one way as they are going in the other direction. And that's what's happening in that copper wire in the other room, or this wire if there's an electrical current flowing through it, which I guess there is. Now, when we're not in electrostatic equilibrium, when there's a current, like this one, ta-da, so there's electrons are slowly traveling through that wire. What do the electrons look like as they're going through? Well, they're going something kind of like this. And what I'm trying to illustrate here is, maybe it bounces like that. Oops. Something kind of like this. So what's happening here, instead of traveling straight lines, there's an electric field. If these are electrons, the electric field is actually going in that direction, right? Because they're, anyways. So the electrons are slowly going in these arcs, right? Because the electric field is changing their orientation a little bit. And what we would see is, actually that one was supposed to be going this way. One of them, I drew the arc the wrong way. I'll show you that. Guys, notice that. They're all tending to arc in that direction. The velocity should kind of also have this randomness to it. But notice what's happening here. Velocity in the x direction, because they're accelerating, the velocity is increasing in the x direction. Now here, it's slowing down, coming to a stop to maybe start going in the positive direction. Let's draw one that does that. It's like, it hits an atom, it goes off in some random direction, but the velocity after it hits it is also changing, right? This one hits an atom, it starts going negative, but then it accelerates into the positive velocity. So it kind of comes to a stop and then accelerates. But the key thing is, notice they're all moving here. And because now each of these, if I took the average of this side of each of these little lines, it will be 0 here. But since they're all tending to increase, if I were to take the average velocity, that's average velocity is, in fact, what we called the drift velocity, which is, okay, they're both black, but the drift velocity is this higher one, right? So it's going to be on average going a little bit in the positive x direction. Where was I going with that? Oh yeah, so taking a look here, what changes when the circuit is closed. So I have a charged capacitor, positive charges and negative charges on one side. If I were to close the switch before electric field is 0, that's going to be kind of this situation. Afterwards, electric field in the conductor is not 0. Now, you got to watch out, because I've said all quarter so far, electric field in a conductor is 0. And I've also said the potential is constant. But that was only assuming that we were in electrostatic equilibrium. Once I close this switch, since there's, a net flow of charges, that's not electrostatic equilibrium. V is going to vary, and the electric field is not going to be 0 inside the conductor. Once I throw the switch, you're going to see an electric field that goes from the positive charges to the negative charges here, right? And that's what drives the current, right? We have an electric field going in this direction. The electrons, I guess, are what go in that direction until the charges are redistributed in this circuit, and then you'll be back to electrostatic equilibrium. Now, something I want to come up with, then we'll use this in a second, is a formula for that drift velocity. Now, a few definitions. Delta V, that's the change in velocity. That makes sense. That's the drift velocity. How much can they change on average? Acceleration times delta T. Well, sometimes the book or various places use tau as the mean time between collisions. This is kind of a common thing. So we replace delta T with tau, and we replace acceleration. What's the acceleration of these electrons? F equals ma. A equals F over m. But we know force is charge of the electron times electric field over m, which would be mass of the electron. And that's where we get this formula for the drift velocity, which we'll use in the next example.